Hi Year 12, so this video will go through looking at the questions that I gave you on the printout for your topic 1 revision. So these are all past paper questions from IB paper 3s. So you can see in the first question there's lots of stuff in here that we haven't covered yet. But with your paper 3, you don't really even need to have covered the physics topics to be able to understand how to look at the measurements and the uncertainties. You should still be able to do that part of the question anyway. So we have a semiconductor device, just here, generating an EMF, which is a voltage, which varies with light intensity. So we've got a diagram showing how this is set up. So a lamp is emitting light, obviously. We change the distance between the lamp and the semiconductor, and we then measure the EMF, this is epsilon, using the millivoltmeter. It then tells you the result. It says the table shows how the voltage varies with the distance. And the first question says, outline why the student has recorded the voltage values, the EMF values, to different numbers of significant digits, but the same number of decimal places. So if we look at the table, you can see the results in terms of significant figures are not consistent. We've got 2 here, but we've got 3 here. And it's asking you to explain why that would be. Okay, and it's to do with the precision of the instrument. So if you think about it, this voltmeter is always recording to the nearest 0.1 volts. Okay, so we say the EMF was measured using a voltmeter that has a fixed precision. Okay, so it's important to reference that. Because the voltmeter reads to plus or minus 0.1 millivolts, the recorded values in the table must have this precision, because that tells us something about the instrument and what we could measure to. So that's more important than keeping the number of significant figures consistent there. Okay, now on looking at the results, the student suggests that the EMF could be inversely proportional to the distance. He proceeds to multiply each D value by the corresponding value of EMF. Explain why this procedure can be used to disprove the student's suggestion, but it cannot prove it. Okay, so let's take a look at what the student actually did. Okay, the student suggests this. Okay, the EMF is inversely proportional, so proportional to 1 over the distance. Okay, that's the same as writing the EMF is equal to some fixed constant multiplied by 1 over D. Okay, those are equivalent with proportionalities. If I multiply both sides of this equation by D, I get EMF multiplied by distance must be K, which we know is going to be a constant value. Okay, so that's why he's proceeding to multiply each D value by the EMF. So when he then takes his values of EMF and distance and multiplies them together, if he finds that they are not giving constant values, he knows he's disproved the suggestion. So with the table, if we multiply 19.1 by 5.5 and get a value and then compare it to 18 multiplied by 6, if the values are very clearly different when we multiply these together, we know that the suggestion isn't true. Okay? If we find that they are very similar, it does suggest that we have an inverse proportionality, but we're not proving it with absolute certainty because we're only testing 6 different values, and it could be that outside of the range that we measured, it doesn't stay constant. So we can't prove with absolute certainty that it is inversely proportional. It only supports the idea, basically. Sorry, I should slow down. So the 2 marks come from explaining why you can prove it's not constant, so when you multiply the 2 together, but also then explaining that if the values are constant, it makes a suggestion that it's possibly valid, but it doesn't absolutely prove it. Okay, and then in the next part, it gives you 3 of the distance values that are in the table, and it asks you to discuss whether or not that EMF is inversely proportional to distance. So I took the EMF values recorded for each of those distances from the table. Literally, you just grab the values. Okay, and I've calculated the values of the EMF multiplied by the distance. Okay, they are very clearly not the same. There is a massive difference. Okay, so I've said these values are clearly so far apart, they disprove the suggestion. EMF is not inversely proportional to D. Now, let's say you got a value of 100, 101, and 98. If we got those three numbers, we could make an argument that they are constant because there's some level of uncertainty in our measurements. And so within uncertainties, those actually might be the same numbers. So they don't have to look identical. I don't need 100, 100, 100. But there needs to be within the uncertainty tolerance for us to say that it is inversely proportional. But clearly our uncertainties are not going to be as large to give us this range. Okay, so you get 1 mark for calculating, 1 mark for stating that they're so far apart, and then 1 mark for saying that it's not inversely proportional. So then it's going to talk to you about a graph with these points. It asks you to firstly draw the data point corresponding to D as 19.1. So literally it's take the 19.1 value and you're going to have to plot the EMF of 5.5. It then asks you to draw an error bar for that point, assuming that there is a constant absolute uncertainty in the D values, and then it asks you to sketch the line of best fit for the plotted points. So I'm just going to zoom out a little bit, I'm not sure if I can get the whole thing in. So you can see a very faint pencil line. This is what I want to see when you're plotting graphs, okay? I don't want to see heavy-handed lines. Let's make my pencil a bit sharper. I don't want to see things like this. I don't want to see things like this. And I certainly don't want to see things like this. Okay? If you push down that hard and you make a mistake, when you try and rub it out, you're going to still see it. Whereas if you do it nice and lightly, let's say I just mess up a little bit, I can rub it out and you wouldn't even know it was there. Okay, so that's the first thing to point out. So I'll zoom in a little bit so we can see our points. We were plotting for D as 19.1, so 19 is here. Each small square is 0.2, so halfway gives me 19.1. And then that tracks along to 5.5. Make sure that you count correctly. Each one of these small squares is 0.4. Okay, for each small square on the y-axis. So long as you are correct to within half a small square, you're absolutely fine. And then remember that it asked you, once you'd plotted the point as a single point, to add the error bar. So you can see, looking at all of the others, it's plus or minus 1 small square. Okay, so just make sure you go to halfway into the next box and halfway into the next box. Sorry, that's probably really noisy. And then don't forget to close off your error bars. Crikey, very loud playing. I think it must be a military one. Okay, next then. All the values of EMF have a percentage uncertainty of 3%. Calculate the percentage uncertainty in the product, d epsilon, that's the symbol here, for the value of D is 18 centimetres. So the first thing I do is look and find my value for 18 centimetres. So if I go all the way back to the start, when it was 18, I had an EMF of 6 millivolts. Okay, so I have a value for distance, I have a value for EMF. I know that my absolute uncertainty in my distance is plus or minus 0.2 centimetres. Now the reason why I know this is because I have plus or minus 1 small square on the x-axis, which is measuring D, and each small square on the x-axis is 0.2. Okay, so that's how I get my absolute value. I take the error bars and I can see that it's plus or minus 0.2. I then need to find 0.2 as a percentage of my value to get the percentage uncertainty. Okay, so I do the 0.2 over the value, multiply it by 100 and I get 1.1%. Okay, and that's in D. But they want you to find the percentage uncertainty in D multiplied by epsilon. So all I'm going to do is add the two percentage uncertainties together. So we've just calculated that it's 1.1% for D, and we're told in the question that epsilon is plus or minus 3. So you add those together and you get plus or minus 4.1% there. Okay, next question. Question 2 says you've got an array of photovoltaic cells, it's basically a solar panel, used to provide electrical energy for a house. When the array produces more power than the house consumes, the excess is given back to the electrical supply. So it's then sent back and other people can use that electricity that's been generated. So the graph below shows how the power produced by the array varies with the time of day, because obviously the sun never changes. The error bars for power supplied are too small to be seen. Sorry, that's for time, but you can see the error bars for power, and you can see they progressively actually get larger as the time goes on. Ignore the sketches at the moment because we haven't seen what the question is. So it says, using the graph, estimate the time of day at which the array begins to generate energy. Now your graph didn't have any lines on, just had the data points plotted. Okay, now in order to work out what time of day the power was more than 0, you need to sketch the line of best fit through the points. Okay, so you can see I've added that as a smooth curve, and where we reach the x-intercept is where the power is 0. So at this point the power increases from 0 and we start to get power produced. So you can see that that's about 8 AM for me. So long as your line of best fit is clearly within all of the error bars, if yours was slightly out, that doesn't matter, they will mark it against yours. It just needs to be to the nearest 6 minutes of your x-intercept. So mine was 8 AM. Okay, in part B, it says the average power consumed in the house between 8 and 12 is 2 kilowatts. Determine the energy supplied by the array between 8 and 12. All right. We know that the area under the graph is going to be the energy produced by the array. We have power on the y-axis and time on the x-axis, and we know that power multiplied by time gives us energy. Okay. Now, because I have a curve, it's not necessarily very easy to get the area under the graph. So there are a couple of ways that you can approach this. You could box off all of the squares that perfectly fit underneath your curve and then add the small squares afterwards that are kind of outside of a very clear pattern. But that might take quite a while. So what I've done is I've added this dotted line over the top, okay, to make a triangle which is very easy to calculate the area of. Now, for the first section, I'm actually basically underestimating how much I've got. But in this section here, I'm overestimating how much I've got. And these cancel each other out. The area of this section is approximately equal to the area of the section above the graph. And so we can basically say that cancels each other out, so the area will be approximately right. Bearing in mind that it does give you a chance to determine the energy, and it's only worth 3 marks, they're not looking for a perfect answer. So we draw our dotted line to give us an estimate, and we work out the time we've got here. So we've got about 4 hours and 4 minutes on mine. Yours might be slightly different. And then we've got 7,000 watts on the Y. So I can then, oh, excuse me, that's falling over. Take my time, convert it into seconds, because it needs to be in seconds to find the energy in joules. And I'm just going to find the area of the triangle. So I'm going to do a half times base times height. So there's my height, there's my 7,000 watts, my 7 kilowatts. And that is my time from here to here in seconds. And I get a value in joules. Okay, so the total energy under the graph I worked out to be 51.2 megajoules. Okay, so that's the first thing I did. I then know, sorry, let's just make it a bit clearer, that the area under the graph, which is the total energy produced, minus the average power that was consumed by the house, must be whatever was left over, and that's given to the array. Okay, now I know that 2 kilowatts was used between 8 and 12 by the people in the house, which is 2,000 joules per second. Okay, and they did that between 8 and 12, which is 4 hours, which is 14,400 seconds. So that's how long we're looking at. If we again multiply the energy, sorry, not the energy, goodness me, the power by the time, we get the total energy used by the house. Okay, so we've taken that average of 2 kilowatts, multiply it by the 4 hours in seconds. This is how much energy was needed by the house. Remember, that's the energy that was produced by the array, which is obviously a lot more than what the house needs. So we just find the difference between the two to give us the energy that's given back to the electrical company. Again, your number might be slightly different because you might have a different estimate of the area, and that's fine. Okay, so long as it's reasonable, you will get the marks. There's a good range that you are allowed. Okay. Then in part C, it says the power P produced by the array is calculated from the generated EMF and the fixed resistance using the equation V squared over R. It tells you the uncertainty in R, and it asks you to calculate the percentage uncertainty in V at 12 o'clock. Okay, so the first thing is at 12 o'clock, we want to find what the power value was. So we go back to our graph, go up to our point at 12. Sorry, you can't actually see that. I'm trying to cram too many things in on the table. So we've got at 12 o'clock, we've got our power rating of 6 kilowatts. Okay, but we also need to know the absolute uncertainty, and that comes from the error bar. And you can hopefully see that that's 2 small squares, which gives us plus or minus 0.4 kilowatts, because each small square is worth 0.2, and we've got plus or minus 2 of those squares. Okay, so I know that my power at 12 was 6 plus or minus 0.4 kilowatts. It tells us that power is equal to V squared over R, but it's asking for us to give a value for the percentage uncertainty in V. So I'm going to rearrange the equation to get V as the subject. So obviously multiply both sides by R, and I get V squared is PR. I square root both sides, and I get V is equal to the square root of PR, which is the same as PR to the power of a half. Okay, now that's helpful because I now know how to accumulate my errors to find my percentage uncertainty in V. I'm multiplying these two things together, so I must add their percentage uncertainties. And then I'm raising that to the power of a half, so I have to multiply by a half to get my overall uncertainty. So I've got a half, because I'm multiplying by the power value, multiplied by the percentage uncertainty in P, and percentage uncertainty in R. So this is my absolute uncertainty that we calculated for P over the value of P. Multiply it by 100, that gives us the percentage uncertainty in P, and we are told the percentage uncertainty in R in the question is 2%, so I'm just going to add those two together, multiply by a half, and I get my percentage uncertainty of plus or minus 4.4%. Okay. If you read yours slightly differently, if you read off the power value slightly differently, you might get a slightly different number, but again, you should be looking at something in that ballpark. Okay, later in the day, a second set of data was collected where we've got p squared on the y-axis, so power squared, and we've got t time in minutes on the x-axis. Using the graph, determine the relationship between p squared and t. Now I already can see that p squared is the y value on the graph and t is my x value. I can also see that I very clearly have a straight line graph. Okay? The fact that we have a straight line graph tells me that the form of the graph is y equals mx plus c, where m is the gradient and c is the intercept. I then need to find those values to be able to give the relationship, because the relationship is defined by the equation of the graph. Okay, so plus c is obviously my y-intercept, which is 8.7, and my gradient is obviously negative, and it's the 8.7 is my change in y over my change in x, which is 210 if I use the whole graph, and you get your gradient value of minus 0.041. And all I'm going to do is write the full equation of the graph out. So p squared for y is equal to m minus 0.041 x t plus c plus 8.7. And this is the relationship between p squared and t. Okay, I think this is the last question. I'm hoping it is. I've been talking for ages. Connie and Sophie investigate the effect of colour on heat absorption. They make grey paint by mixing black and white in different ratios. Identical tin cans are painted in the 5 different shades of grey. They put an equal amount of water at the same initial temperature into each can. They leave the cans under the heat lamp at equal distances from the lamp. And then they measure the temperature increase of the water in each can after 1 hour. Connie suggests that T is proportional to B. Okay, so we can express that like this, where B is the percentage of black paint. To test the hypothesis, she plots a graph of T against B, as shown on the axis below. Negligible uncertainty just means so small you can ignore it, and the uncertainty is in T is shown, so we've got error bars there. So again, you can see I've got a very faint, smooth curve of best fit. It firstly actually asks you to state the value of the absolute uncertainty in T. Now if you look, it's plus or minus 1 small square and 1 small square on the y-axis, sorry it's a shocking line, is plus or minus 1, so that's why we've got plus or minus 1 degrees here. Then it asks for you to comment on the fractional uncertainty for the measurement of T when B is 10 and B is 90. Okay, so I read off when I have B 10 and 90 here, and I get my temperature values, and I've written them here. Now the error bars are the same size for both of them, so the absolute uncertainty in the temperature remains the same. It's always plus or minus 1 degree Celsius. Okay, the fractional uncertainty is the absolute uncertainty over the value. Okay, so we've got 1 over 33 for when B is 90 is the fractional uncertainty, and 1 over 14 when B is 10. Okay, quite clearly 1 over 33 is smaller than 1 over 14. Okay, so the fractional uncertainty in temperature is smaller when B is larger, when B is 90, which we can quite clearly see even without writing the calculation. 1 as a proportion of 33 is much less significant than 1 as a portion of 14. Okay, so you get 1 mark basically for getting the values and writing the absolute uncertainties, and then 1 mark for comparing the values of the fractional uncertainty. Then you get 1 mark for your line of best fit for the data. Your line has to cut through every single error bar. If you go outside of any of them, you will not get the mark. Okay, always make sure you're going through all of them, please. Alright, outline why the data do not support the hypothesis that T is proportional to B. Well, if T were proportional to B and I plot T and B, I should expect to see a straight line graph. Okay, that's the only way I can prove proportionality. But quite clearly that is not a straight line. If I get my ruler to make it even more obvious, that's not a straight line. You may well have attempted to draw a straight line if you forgot that it needed to go through the error bars, and that should be a bit of a clue to you here that you've probably drawn your line of best fit wrong. So always use other questions to help you correct any mistakes. Okay, so we say if they were proportional we would expect a straight line. The line of best fit is a curve, so it doesn't support the hypothesis. Sophie suggests that the relationship between t and b is of the form t is equal to kb to the half plus c. Hopefully you can see that this is in the form of y is equal to mx plus c, so it will be a straight line graph if I plot t on the y-axis and b to the power of the half. Okay, so that's shown on the next page, and it was here. There was one line, the best fit line. Okay, and it asks you to use the graph to determine the value of c, which is the y-intercept, with its uncertainty. Okay, so the first thing is you actually read the intercept from the line that was already there. Okay, and I've got that as 4.5. So then, to find the uncertainty, I have to draw my worst fit lines on. Okay, so you go from the bottom of the bottom error bar up to the top of the top one, and then vice versa, top of the bottom to bottom of the top. Okay, plot both of those, and you're looking for the distances from the best fit to the worst fit, and whichever one's largest gives you your uncertainty, but you can see we've actually got an equal distance here. So the best fit minus the worst fit gives us plus or minus 2. So that is my uncertainty in the intercept. So I quote C intercept as 4.5 because that's what I read it as, plus or minus 2 degrees Celsius. Now for the fourth mark, I need to make sure that my value and uncertainty have the same precision. So just round this up to 5. 5 plus or minus 2 degrees Celsius. Okay? Because you should be able to measure both the uncertainty and the intercept, to the same precision. Then it asks to calculate the unit of k. So we saw on the previous page that k was the gradient of the graph. Okay, so that gives us y over x, or change in y over change in x is k. Now y is measured in degrees Celsius, but b to the half is unitless. So we're just doing degrees Celsius over no unit. That just gives us degrees Celsius. So the unit of k is also degrees Celsius. And we're done. Hooray!